Welcome friends, Igor is here, and in this video we will discover some basic properties of eigenvalues and eigenvectors. In this lesson we will prove that eigenvectors corresponding to distinct eigenvalues are linearly independent, show that non-singular matrices cannot have zero eigenvalues, and we will investigate properties of algebraic and geometric multiplicities of eigenvalues. Let's get started. First, let's prove that eigenvectors corresponding to distinct eigenvalues are automatically linearly independent. We have a set of p eigenvectors of a matrix A, and the eigenvalues that correspond to these eigenvectors are all distinct. To prove that the set of these eigenvectors is linearly independent, first, let's consider the case when p is equal to 1. The set S contains only one vector x1. By the definition of eigenvectors, the eigenvector must be a non-zero vector, and we know that a set which contains one single non-zero vector is indeed linearly independent. Now, it remains to consider the case when p is at least 2. This is going to be a proof by contradiction. We are going to assume that the set of p eigenvectors is actually linearly dependent. And here is a trick. We know that if we take only the first vector x1, then this set is linearly independent. Then we will add one vector at a time. We add vector x2 to the set, then we add vector x3, and so on. We assumed that by the time we reach the vector xp, the set becomes linearly dependent. So let's catch that exact moment when the set switches from linearly independent to linearly dependent. Let's say all the way up to vector xr the set remains linearly independent, but once you add one more vector xr plus 1, the set becomes linearly dependent. This change in behavior must occur because we start with a linearly independent set, it only contains x1, and we end up with a linearly dependent set. This means at some point the set did become linearly dependent. So the set of eigenvectors x1 through xr plus 1 is linearly dependent. This means there is a non-trivial relation of linear dependence on this set, and we create such non-trivial relation. Then we are going to multiply both sides of this vector equation on the left by the matrix A. On the left-hand side, we are going to use properties of matrix operations, and on the right-hand side, we observe that matrix A times vector 0 is the zero vector. But now we are using our assumption that the vectors xi are the eigenvectors of the matrix A with the eigenvalues lambda I. Here's what we are going to do next. We are going to go back to this non-trivial relation of linear dependence, equation star, and now we are going to multiply both sides of this equation by the scalar lambda r plus 1. On the right-hand side, the scalar multiple of the zero vector still remains the zero vector, and on the left-hand side, we use the properties of vector operations to distribute this scalar multiple. Then we are going to subtract the resulting equation from the vector equation double star. And once again, using properties of vector operations, we can rewrite this equation in the way shown here. But now the term that involves vector xr plus 1 disappears from this equation because the vector gets scaled by the zero scalar. But what we have now is a relation of linear dependence on the smaller set, the set of eigenvectors x1, x2 up to xr only. And our assumption is that this smaller set is linearly independent. Therefore, the only relation of linear dependence on this set is the trivial one, and all scalars in this relation must be equal to 0. Notice that in this proof, we have not yet used the assumption that all eigenvalues are distinct. Now is the time to use this assumption. All the differences of the eigenvalues in parentheses are not equal to 0. Therefore, all alpha scalars must be equal to 0. With this information, let's go back to the original relation of linear dependence on the set x1 through xr plus 1. We just proved that the first R scalars must be equal to 0, and therefore this relation actually looks like this. But a scalar multiple of a vector is equal to the 0 vector only when the scalar is the 0 scalar or the vector is the 0 vector. However, xr plus 1 is an eigenvector, therefore it is not the 0 vector. And so the only way for this relation to be true is for the scalar alpha r plus 1 to be equal to 0. So we just proved that all scalars from alpha 1 up to alpha r plus 1 must be equal to 0. But this contradicts our assumption that we had a non-trivial relation of linear dependence, which meant not all of these scalars could be equal to 0. This contradiction was caused by our assumption that the set of eigenvectors is linearly dependent, therefore it must be linearly independent. Next, let's prove that a square matrix is singular if and only if 0 is one of its eigenvalues. We can prove this if and only if statement using a chain of equivalences. First, we use the definition of a singular matrix. Then we write the 0 vector as a scalar multiple of the vector x by the 0 scalar. But this is equivalent to saying that 0 is an eigenvalue of the matrix A because there is a non-zero eigenvector that corresponds to this eigenvalue. Because this was an if and only if statement, we can also rephrase this as follows. A square matrix is non-singular if and only if 0 is not one of its eigenvalues. Next, let's obtain some additional information about algebraic and geometric multiplicities of eigenvalues. First, let's observe that the characteristic polynomial of a matrix has degree equal to the size of the matrix. This simply follows from the definition of the determinant. But the fundamental theorem of algebra says that any polynomial of degree n with complex coefficients has exactly n roots in the field of complex numbers. The number of roots is exactly n if you count them with multiplicities, and in particular this means that a square matrix of size n has at most n distinct eigenvalues. But the number of eigenvalues is exactly n if you count them with their algebraic multiplicities. If a square matrix A of size n has k distinct eigenvalues and k cannot exceed n, then the sum of the algebraic multiplicities of all these eigenvalues is precisely n. The characteristic polynomial factors into the linear factors where each factor corresponds to one of its roots. And algebraic multiplicities of eigenvalues are precisely the powers in these factors. Now, the polynomial on the left-hand side of this equation, the characteristic polynomial, has degree n, and the degree of its factorization, the polynomial on the right-hand side, is the sum of the algebraic multiplicities of all eigenvalues. Therefore, the sum of the algebraic multiplicities must be equal to n. In one of the previous videos, we worked out an example where algebraic multiplicity of each eigenvalue was equal to its geometric multiplicity. But in general, they are not necessarily the same. However, the geometric multiplicity never exceeds the algebraic multiplicity. The complete rigorous proof of this fact takes a little bit of work, so let me outline the basic idea why it works. Let's denote the geometric multiplicity of the eigenvalue lambda by G. Then, the eigenspace of the matrix A corresponding to this eigenvalue lambda has dimension G, and therefore we can find a basis of this eigenspace of size G. Using this basis, it is possible to construct a non-singular matrix S, which has a property that the product S inverse AS has this special form. The characteristic polynomials of the matrices A and S inverse AS are the same. We will prove this in the next video. And the characteristic polynomial of this new matrix is equal to lambda minus x raised to the power G multiplied by the characteristic polynomial of the matrix T. But this means that the characteristic polynomial of the matrix S inverse AS and in particular the characteristic polynomial of the matrix A is divisible by lambda minus x to the power g. It might be divisible by the higher power of this term because it might also be a factor of the characteristic polynomial of the matrix T, but at least we know now for sure that the algebraic multiplicity of lambda is at least g, which is the geometric multiplicity of lambda. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will discover how changing a matrix affects its eigenvalues. I will see you later.